Okay, so for question one, this is a sort of classic truck and trailer situation. And the first question, we can look at all the details, but the first question is asking us to work out the acceleration of the car and the trailer. Okay, so let's simplify this diagram to start with. If I just have a single block, and that includes all the mass involved, so we don't need to worry about the tension, just model it as one particle. I have 1,250 kilograms, the driving force is 5,000 newtons, and the overall resistive force is just 100 newtons, okay? So if we model it as one particle, it makes our life a lot easier. So I start with F equals ma, 5,000 minus 100 equals 1,250 times by A. Okay, so we've just resolved the force for this part and written the mass times acceleration here. So this gives us 4,900. If I divide this by 1,250, I get my acceleration, which is 3.92. Okay, don't forget a unit. That's your acceleration. So that's the acceleration for the whole system. So we're just going to look at one part of the system now. So to find the tension in the tow bar, what I'll do is I'll just look at this part here that I've circled. Okay, so I'm sort of going to zoom in just to this bit. I could do it for this front, for the car as well, but I usually do the second one. It's just sort of habit. So if I redraw the trailer, let's look at the forces on the trailer. So the force on the trailer are T in this direction and the resistive force of 100 newtons in this direction. Its mass is 250 and the acceleration is 3.92. Okay, so just by zooming in on this bit, we can work out the tension. Again, very similar to the first part, resolve the forces. I have T minus 100, and that equals 250 times by 3.92. So 250 times 3.92 gives me 980, which I'm going to add 100 to, and I get my tension equals 1,080 newtons. Okay, notice how if this number here was bigger, if the resistance was bigger, our tension would get bigger as well. Okay, so the more resistance here, the more tension in the tow bar. Okay, for part B, after 30 seconds, the car stops accelerating and maintains a constant speed. So constant speed is the important part of this question. We know that constant speed means that our acceleration is now 0. So what is the driving force on the car? Well, for it to have a constant speed and the acceleration to be 0, everything must be balanced. So the driving force must balance out the resistive force. So the driving force must therefore be 100 newtons. Hopefully that makes sense. If it was 0, big misconception is that the driving force is now 0. That's wrong. If that was true, then the whole thing would be decelerating as a result of this force here being greater than the driving force. Okay, so the force must balance for it to be at a constant speed. Part 2. So if we look through this like we did on the first question, let's see what happens. It should come up with quite a kind of expected result. We have 250 kilograms, tension in this direction, resistive force is still 100 newtons, and we write T minus 100, and that equals 250 times by 0, because there's no acceleration. So this gives me T minus 100 equals 0, therefore my tension must be 100 newtons. And that should make sense, because the whole way through the system, everything should be in equilibrium. The tension needs to be 100 because the resistance is 100. The driving force must be 100 because the resistance is 100. Okay, and in the gap between them, the two tensions, terrible drawing, sorry, between the car and the trailer, they're both 100. So there's 100 in this direction and 100 in this direction. So they sum together to equal 0 as well. So for the second part, we have an equilibrium situation. And if that happens, acceleration 0, all the forces must balance. Okay, so reading the question, the first thing to add to this diagram is this here. So we have a retarding force on the second particle of 80 newtons. So let's put that on here. So what we don't know is we don't know what the driving force is, but we do know that the acceleration of the whole system is 3 meters per second to the minus 2. So let's consider the whole system together. So we have 650 kilograms. We have a force in this direction, which we're calling Fd. We have a resistance in this direction, which is 80, and the acceleration is 3. Okay, so we know that we have Fd minus 80 equals 650 multiplied by the acceleration, which is 3. So this gives me 1,950 newtons, which I'm going to add the 80 to. So my driving force must be 2,030 newtons. So it's a bit of a kind of work backwards question, this one. Now, the tension in the cable, let's do exactly the same thing. Just draw the trailer, draw the second particle. We have a tension to the right. We have 80 newtons to the left. Its mass is 150, and the acceleration again is 3. So we do T minus 80 equals 150 times by 3. And if I solve for T, I get 530 newtons. Okay, so for part B, again, continue the theme of working backwards. The tension in the cable is now 700 newtons, so we want to work out the acceleration of the system. So starting with our second particle, I know that the tension is 700. The resistive force is still there, it's 80. I don't know what the acceleration is, so I'm going to write 700 minus 80 equals 150A. So this gives me 620 divided by 150. So the acceleration of the system is 4.13. Okay, so finally, the force applies to the first particle, so the driving force on the car. We need to think about the acceleration first. So the force minus 80 is going to equal the whole mass, which is 650, multiplied by 4.13, which is the acceleration of the whole system. And that gives me an answer, once I've added the 80 on, of 2,766.7 newtons. Okay, so these are all work backwards questions. And to make sure that you're on the right track, it'd be a good idea to put this answer back in and make sure you get the correct acceleration out. Okay, for this question, we have a car and a caravan. I'm going to label up all the information on this diagram first. So the car has a mass of 800 kilograms. The caravan has a mass of 400 kilograms. If we look at the resistances on the caravan, we have an air resistance of 400 and a frictional force of 100. So let's combine those. That gives us 500 newtons. Okay, this is our Towbar here. And so we have tension going in both directions from here. The driving force on the car I can label on here, and I will call that FR. Okay, so the first question, the car provides a driving force of 5,300 newtons. What is the acceleration of the car and the caravan? Again, let's combine them. So we have one particle of mass 1,200. Driving force is 5,300. The resistive force is 500 newtons. So quite simply, we use F equals ma, 5,300 minus 500 equals 1,200 A. This becomes 4,800. The calculation I do is 4,800 divided by 1,200, and it shouldn't take a calculator for you to see that that is 4 ms to the minus 2. So the acceleration is 4. Okay, what's the tension in the tow bar? This time, just to show you that it works both ways, I think I'll use the car as the example. So let's isolate the car. Car's mass is 800 kilograms. It seems a bit weird, but caravans are actually very light. Most of the weight is in the axle and the chassis under here, and the rest of it is sort of fiberglass and air, so it's actually not that heavy. But let's look at the car. We have a driving force of 5,300. In this direction we have the tension. The acceleration is 4. So to work out the tension, we do 5,300 minus T, and that equals 800 times by 4. Okay, so we move it around a bit. We end up with T is going to equal 5,300 minus 800 times 4, which is 3,200. And that leaves us with a tension of 2,100. So just for an opportunity to do this, I'll show you that it's the same for the Caravan as well. So the Caravan here has a mass of 400 kilograms. Tension this way, resistance is 500. So for this one we do T minus 500 equals 400 A, and we get exactly the same story. T equals, in this case, 1,600 or 1,600 plus 500, which is 2,100 newtons. So that's just to show you that it doesn't matter which one you choose, you get the same tension between them. Okay, and that is Newton's third law, because we have an equal and opposite tension in both directions. Okay, so we're told that the tow bar will break if it experiences 18,500 newtons or more. That's a lot of force, a huge amount actually. But let's see what the maximum driving force we can apply is. So if we set this up as kind of working through the same equation as before, but we say that the tension is this amount. So we'll say that T equals 18,500. That will show us what the maximum force is going to be. So let's go for the car in the first place. So what we could do is we could say that FD minus this tension, which is 18,500, is going to equal 800 times A. Okay, so we've got an equation we can write. Another equation we can write is if we look at the whole system, we could say that, well, FD minus 500 is going to equal 1,200A. So we have two equations here with two unknowns. We don't know what the force is and we don't know what the acceleration is. But you can solve this in whatever way you want, label them up 1 and 2. What you should find is, as a result of this, you get an acceleration of 45 meters per second, which is incredibly high. And if you then follow this through, you get a maximum force that can be applied of 54,500 newtons. Okay, so in order to break or to sort of snap this tow bar, we're going to have to apply a huge amount of force. Okay, but just set up the equations as I've used before, solve them simultaneously, and you should get to these answers. If you get 54,000, you've possibly just forgotten to add on this 500 in the last step. Okay. So in this problem we have a sort of multi-carriage problem, a multi-trailer problem. So we have two tensions, and these will be different when the whole system is accelerating. So we need to make sure we can work this out. You can actually extend this problem to a kind of any number of carriages. It's not too complicated, but we've got to be really careful when we make these calculations. So as usual, the first thing is to label this diagram up, and then we're going to work out the acceleration. So we know that the resistive force on A is 100 newtons, and the resistive force on B is 75 newtons. Okay, maybe slightly less because it's behind this one, I don't know. But that takes into account air resistance and friction. Okay, so the acceleration of the whole thing, we should be fairly used to this by now, so I'll go through it quite quickly. We have the resultant force, which is 12,000 minus 175, and that equals the total mass, which is 1,560 times by the acceleration. Okay, so working this through, this gives us an acceleration of 7.58 ms to the minus 2. Okay, so we should be quite used to doing that by now. Okay, so for tension 1, well, the first thing to think about is which of these tensions is going to be bigger, and hopefully it stands to reason that this tension is going to be bigger because it has this mass and this resistance and this mass and this resistance. So it has both of these, whereas T2 only has one. So what we're going to do is we're going to actually sort of lump these two trailers together. So we're going to put a circle around these two, and we're going to sort of combine them together. So what we'll do is, if I draw a really quick sketch, I've combined them together so they have a mass of 560 kilograms. T1 goes this way. The resistive forces are in total 175 newtons, and the acceleration is 7.58. So to work out this tension, we do T1 minus 175, and that equals 560 times by the acceleration, which is 7.58. So we times these together, add the 175, and that should give us our tension, which is 4,419.87. So let's call it point. What's going on here? Let's call it 0.9. Okay. For T2, sorry if this diagram gets a bit messy, we're actually just going to look at what's in this green circle. So we're just going to look at this last carriage. So in this case we have T2 minus the resistance, which is 75 only, and that equals the mass, which is 260, times by 7.58. Okay, so this gives our T2 as 2,045.8 newtons. So this kind of goes in line with what we were thinking. We thought the first tension would be more than the second, and it's been borne out in our workings. Okay, so that tension is greater than that one. Okay, let's have a look at the last part of this first part of this question. D. After accelerating for 10 seconds, the train maintains a constant speed. So whenever that comes up, that's a big sort of alarm bell should be ringing. That means one thing, and it means that acceleration equals 0. And we have an equilibrium situation. So we are in equilibrium. Okay, so if we're in equilibrium, then it means that the resistive forces and the driving forces are equal to each other. Okay, so the driving force from the train must be the same as the resistive forces. So the driving force must equal 175 newtons. Okay, what are the tensions in the couplings? Well, we could make an assumption here, or we could just make sure that it does work. So let's look at the last carriage just to kind of make sure that our guess works. So for the last carriage, 260 kilograms, tension this way, 75 newtons that way, we can write that T minus 75 equals 260 kilograms times by 0. Therefore, T must equal 75. Okay, so the tension in the second coupling is equal to the resistive force, and the tension in the first coupling, not difficult to work out, is you add those two together. So in this case, T2 is 75 and T1 is 175. Okay, again, remember, we're in equilibrium, so those forces must balance. Okay, a bit of an extension question for you, this, but one that needs looking at. If we start thinking about thrust, now thrust is the opposite of tension. If a tension goes like this, then the thrust is the opposite. A thrust is when something is being compressed or pushed together. So we get thrust in tow bars when we brake. When we brake, the two carriages here are going to push this way into the back of the engine. Okay, so when we decelerate, we get thrust in these tow bars. Now, thrust is just as important as tension. Thrust can cause damage, and we need to build things that can withstand thrust forces. So to start with this, we're going to decelerate. So this force is now gone, and there's a braking force of 5,000 newtons. So we can label this in this direction. I don't know why I keep saying that. Let's try that again. Like this. Okay, so we have 5,000 newtons going this way, and this is because of the brakes. So the brakes are going to create a 5,000 newton braking force. Now, first thing we can do, as probably you're getting used to this method now, is that we find the acceleration to start with. So to find the acceleration, we need the resultant force, and we need the whole mass of everything involved. So the resultant force is going to be 5,000, in this case, plus those resistive forces from the carriages. Now it's plus because they're all acting in the same way now. They're acting to the left in this case. So the 5,000 is acting this way, so are these resistive forces. So our F is going to be 5,175. Okay, the overall mass is 1,560, and the acceleration is A. So the deceleration, or the acceleration, is going to be 5,175 divided by 1,560. Now, the way that we go about this is up to you. What I'm going to do is I'm going to say the acceleration is minus this divided by this. So it's minus 3.317. But you could say that it's positive. You just need to make sure it's going in the right direction. So the direction of this acceleration is accelerating to the right with negative 3.317, or it's going this way with positive 3.317. It's really important you understand that. A deceleration is just a negative acceleration. But if you want to keep labelling it with an A, you need to use a minus. Okay? So we've got a negative acceleration. That makes sense. We're slowing down, our speed is being reduced. So with this in mind, we use the same method, but we have to be incredibly careful with our negatives now. So here's this question here, the force from carriage A on the train, so from here to the train, the thrust in this tow bar here, we need to work out. So we're going to consider, to make our lives easier, we're just going to consider the engine, okay, so the front of this diagram. So that is 1,000 kilograms. We have a force acting in this direction of 5,000. And we have a thrust, it's being pushed in this direction. Okay, so the thrust from carriage A is pushing this direction, so it's the opposite to this braking force. The acceleration goes this way. Okay, so it's 3.317 in this direction. So we can probably see we're going to have to resolve this in the right way. So I'm going to resolve by saying that to the left is positive. So I'm going to say the resultant force is 5,000 minus T1, because that's going the other direction, and that equals 1,000 times positive 3.317. Now you could go the other way around, that's completely up to you. You could have T minus 5,000 equals 1,000 times minus 3.317, but just whichever way you go around, make sure you get the negatives correct. Now if I do it this way, I can add this to this side, so I end up with 5,000. I take away my 3.317 from this side, and that gives me my T1, which is 1,683 newtons. Okay, if your answer comes out negative, you've probably done something wrong. Okay, so for the final part of this, we're looking at carriage B and what that's doing to carriage A. So let's draw carriage B. That is 260 kilograms, and it's going to exert a thrust. So the thrust is going to push in both directions. So the thrust is going to go this way. Okay, so let's call that T2, and its resistance, so 75 newtons, its resistance to motion is 75 newtons that way as well. Okay, so we can keep everything positive for this one. It seems obvious which way we're going to make positive. We're going to make the left positive, otherwise we'll have two negatives here. So we can say that the acceleration is in this direction, 3.317. So if we set it up, we're going to say that T2 plus 75 equals 260 times by 3.317. Okay, so when you times that and then you take away the 75, we get a T value of 787.42 newtons, or to say 0.4 newtons. Okay, notice how the 75 in this case is actually reducing the thrust. Okay, it's sort of working in the same direction as it, so it reduces it. Okay. Good. So when you have tension, you have thrust, and make sure you can calculate with both. Okay, so the first question is to draw a free body diagram. So I'm going to start with a surface here, and I'll have my boat like this, and my skier is a lovely little block like that. Okay, so they're attached with a cable like that. So I need to label up all the forces that I have and the masses. So the mass of the boat is 400 kilograms. The mass of the water skier is 70 kilograms. The tension's in here, so we need to label this like so. The driving force of the boat is 2,110, so let's put that there. The resistive forces, so for the boat, we have a resistive force of 400 newtons, so a drag of 400 newtons. For the water skier, we have an air resistance of 100 newtons, and we have a drag from the skis of 200 newtons. It doesn't really matter where you label this, just if it's a friction, it's lower down, if it's an air resistance at the top, makes a bit of sense. Okay, so I think that's pretty much it. We don't have to label normal forces at the moment. We'll come on to that when we look more at friction. But for the moment, that's pretty good. Okay, so what's the acceleration of the boat and the water skier? Well, for this, we combine them. So we have 470 kilograms. The force to the right is 2,110 newtons. The force to the left here, well, we've got a few to combine. So we've got 100 here, 200, and we've got 400. So if we combine them together, we get 700 newtons. Okay, so using F equals ma, 2,110 minus 700 gives us 470A. And if we work that through, we get A equals a nice round number, 3. Okay, B done. What's tensions in the tow rope? Well, let's label up what we want to look at. So I'm going to choose the water skier. So I'm going to circle this bit and just zoom in on this situation. So my water skier, 70 kilograms. My tension this way is T. The resistive forces are 300 newtons. The acceleration is 3. So I do T minus 300 equals 70 times 3, which is 210. I add the 300 across, so I get a tension of 510 newtons. Okay, it's always good to check with the other particle as well, so you can check with the speedboat and see if you get the same tension. Okay, last part, so part D. They're travelling at 20 kilometres an hour. The water skier loses their grip. How far do they travel before they come to rest? So what's important now is, and you'll see examples of these questions, essentially this has split. So our tension is now gone. Okay, so we're left with our water skier with no tension this way. The only forces acting are the resistive forces, which are now going to have quite a drastic effect on the water skier's speed. We don't know what the acceleration or the deceleration is, but we can work it out. So again, F equals ma. The force is 300. The mass is 70. So the acceleration is going to be 300 divided by 70. Let's call it 30 over 7 for the moment, just to be accurate. Okay, so it's 30 over 7 meters per second to the minus 2, and this is a deceleration, so I'm going to put a negative in front of it. So because we've removed the tension, the resistive forces are divided by the mass, and that gives us the deceleration here. So we're going to be slowing down at quite a rate. Now, how far do they travel before they come to rest? Well, this is a SUVAT question. So with SUVATs, let's always start by listing SUVAT, seeing what we've got and what we need. So we're looking for S. U is 20 kilometers an hour, which, if you convert it, becomes 5.5 recurring meters per second. V is 0 because we're slowing down to rest. The deceleration is minus 30 over 7. And we don't really need T, so let's just get rid of T. Okay, so looking at what we've got here, S, U, V, and A, I would be tempted, well, I would use one that we use a lot, which is V squared equals U squared plus 2AS, and I would rearrange this. So I'd write that S equals V squared minus U squared divided by 2A. Obviously, V is 0, so that goes. I end up with my U squared, which is 5.5 recurring. Apologies for going between recurring and fractions, that's not great, but whatever. Over 2 times the acceleration, which is minus 30 over 7. Okay, so the nice thing is the two negatives are going to cancel. If you've missed that, if you've left one of the negatives in and not the other, you're going to end up with a negative result. So make sure that both negatives are there, and that gives us a result of about 3.6 meters. Okay, now in maths it's always a good idea, well, mechanics it's always a good idea to make sure your answer is realistic. This means that the skier is only going to travel just shy of 4 meters before they come to rest. Okay, 5.5 meters per second is not that fast, and the resistive force is really quite strong. So I think this is quite realistic as an answer. If they let go of the towing rope, they'll come to rest pretty quickly. The other thing to think about is assuming they stay upright. Chances are they probably won't stay upright, they'll probably fall, and that means they'll slow down much quicker.